Okay, so if I'm not wrong, last lesson we ended with this kind of things. So the first language is the Algol and the Lisp machine. We have now to to switch to a physics part. I mean, the introduction of solid state electronics, which was clearly a revolution in the computer field. So we have this is in Italian. Why? Maybe I'm wrong. I have opened the Italian version of the slides. Computer history. Maybe history computer. History. This is not history computer. Where? History computer 3 should be this one. Okay, so this one. So we have to introduce the idea of semiconductors, which is a field which can say appassionate physicists, I don't know, engineers. So the idea is that in a crystal there are bands available to the outside electrons, which are populated up to a valence band, and then depending on the material, we can have a gap. I mean that only if you furnish enough energy to electrons, they can jump from the valence band to the conduction band, and this is essentially insulator. I mean that they can say conduct, but only after a breakdown, which normally implies the destruction of the material. While for conductor metals, there is a continuous available number of levels from the valence band to the conduction band, and so they can conduct electricity without any problem. Clearly, in the middle, there are semiconductors which have a gap of the order of some electron volt, so that with the given a sufficiently high field, they can conduct. And okay, these are semiconductors. What we do is to add different atoms, so to dope the semiconductor with a given type of atoms, which can be of two character. First one with less electron available for the conducting band than the original one, or with more electrons. In this case, in case you have less electron, you have essentially a void vacuum, so that other electron can jump here, which is essentially the same as thinking as the gap to jump from in the opposite direction. So they are called the doped semiconductors of type P, since they have positive charges, which are actually these holes that can travel along the lattice. On the other side, you have lattice with some atoms replaced with another one with more electrons. So they have a free charge of type N negative that can travel. Remember that the lattice is anyhow neutral, so that if you have a positive hole here that jumps away, leaves here a negative charge, and vice versa in the other case. Okay, so now if you now join a semiconductor of type P with, for instance, a semiconductor of type N, also with a pure semiconductor, but let's consider only these two types, you have in some sense the same as when you have a semi-permeable membrane between two solutions, for instance, water and water with salt. The semiconductor membrane is something that allows, for instance, the ions of salt to pass, but not to water molecule. So an atom, so an ion can pass because of the diffusion. So essentially, it is an entropic force. On the one side, there is a lot of ions, and the other side there are very few or nothing. And so it tends to pass, but then doing so, it creates a force that brings it back. And the same happens here. In this p-doped semiconductor, you have an excess, so you have a lot of free positive charges that tend to diffuse into the n-type semiconductor. And the other opposite things happens in the reverse direction. So this continues until here is the other. I allowed her to join, but I don't see her. Okay, so this happens until there is a sufficiently high potential difference that brings these charges back. Okay, Heizen. And so at a final conclusion, you have a positive, a potential difference between the two joined semiconductors. In this case, clearly, if you try to conduct currents in one direction, you increase this part, which is essentially composed by charges of the opposite type, while in the other sense you are reducing this. And so at the end, this junction works like a diode. So it allows the current to pass only in one direction. Clearly, you have to pay a small amount of voltage. So essentially, this is the characteristic. Normally, it is almost insulating, trying to polarize it with with the opposite field. If you go in the right direction, you at the beginning nothing or almost nothing happens. At a certain point, you have an almost free passage of charges. This voltage difference is about 0.5 for German and 0.7, 0.8 for silicon. Clearly, on the opposite part, there is a voltage after which there is a sudden conduction with almost no resistance. And so, in general, if if the diode is not prepared for doing that, this means a breakage of the diodes. But there are a lot of diodes that works exactly in this field, but we are not really interested in this moment. And clearly, using two diodes in series, you can build a transistor. So essentially, a transistor works in this way. You have you have a different, essentially it is like having two different diodes in opposite directions. So in principle, no current should pass from either direction. But if you inject charges from here, these charges reduces the void part of these diodes and allow a large current to pass from the emitter to the collector or vice versa. So we are not entering these details. There are two types of transistors. There is other types of transistors which are called the field effect, which works much more like a faucet, no? Because in this case you have the source and the drain in this way, and you use the void part here in order to reduce the channel from which the electrons can pass, or electrons or charges can pass. So this is a more, say, mechanical way of considering a transistor. But these are quite important because they can be built in planar way. So these, you see here, you have the source and the drain, and by acting on this gate with respect to the substrate, you can close or open this channel, and in this way you can build a transistor only depositing things on one side instead of joining like in this case. And clearly this is the how large large integrated circuits are done nowadays. So just after this quick introduction to the world of solid state physics, after the introduction of transistor in, say, they are quite old, 48, they took a rather long amount of time, say 10 years, before being introduced in the computer field. So the Philco and the AT&T were the first to introduce a transistor. Remember that at that time the transistors were physical, so separated, sold on the cards. For instance, I once visited the Elea, Olivetti Elea, nearby Florence. There is an example in one high school. And then they have rack and rack of cards. Each card has a couple of transistors, not much more, with a lot of resistors and so on. So it took clearly, say, one card is one logic gate or one unit of memory. So you can imagine how big they are. And clearly, those like IBM who were specialized in building computers using valves or a vacuum tube, they started, which were clearly also reducing in size, so reducing in consumption. They tried first to react using the same model, but finally they were forced to switch to solid state. Clearly, as always, it is not easy for a company to replace the background. And so these are the computers that you see, for instance, in the, I don't know, Dr. Strangelov, the center, the control center of the USAF center. But at that time, if you can see here, there had no consoles, clearly no videos, but essentially also the idea of a console in which you can type command was not still introduced. Essentially, they were based on switches or buttons from which you could run one program or another, but not, say, with an interpreter with really a front end. And clearly, everything was stored on punched cards for the IBM or tapes, and they clearly were increasing the capacity. Clearly, now that the capacities of computers were increasing, clearly one started to wonder if there could be a better way of programming them, because clearly you had to, first of all, you have to train a lot of people in writing programs because there was a demand on this. But as you may imagine, in order to become proficient in programming, you have to try a lot of different solutions, which was not the case for the first approaches, because as far as you are considering only problems in the field of physics, you had essentially everything already clear in mind what kind of computation you have to do, and you have just to translate this into the language of computers. But with computers, you can do a lot of different things. for which you had no standard procedure. You had to invent them. But inventing a procedure means also trying, and this was not really easy with such a mainframe. We shall see that this will open the field to small machine and school of machines. No? And clearly, at that time, the programmers were essentially women because, first of all, most of them have been trained to typing, and so they were handy in punching cards. And then it was considered they were more, say, cautious. Okay, another point that was not clear at the time was what should be the smallest amount of computer memory to be addressable in the single way. Because at the beginning, when you only considered the numeric computation, you just had a certain size for numbers, and that was all. Then they started to realize that if you want to say count small numbers, it is wasting memory to have, I don't know, 30, 40, 60 bits just to store, say, some units. But on the other hand, if you want to be able to address, say, at the level of bytes, you should now, if you want to store a larger number, to use more bytes, so you have to manage this. So at the end, the idea is to have more flexibility in addressing the memory, so that they started to consider the idea of addressing different amounts of memory, bytes, words, and double words, and so on. And so also the size of a byte was not really clear. There have been computers with the byte made by 9 bits or 8 bits or even 7 bits, and so on. And clearly, this was also the age of Thomas Watson, the CEO of IBM, whose motto was think before act. And he was really a curious man. For instance, at a certain time, he announced something, I don't know, this 70-30, that should be 60 times more powerful of the previous one, at the cost of, say, not really, candies, 30 millions, but several problems implied that the performance were only half. And clearly the reaction, essentially publicity action, was that he announced that the price was halved in two because of these performance issues. Clearly, since this meant losing money, he only delivered the machines already prepared and then stopped the delivering. And but this failure opened the path to the real revolution, the System 360, which was, as we shall see, the real standard for mainframes. Then another innovation of this time was the virtual memory. Now, because the idea is that these computers has a fixed amount of memory, but it was really very problematic to manage the memory. It meant that you had to keep track when you wrote a program to how many memory was using at every point, in order not to pass the limit, and clearly maybe delete something or write something to some device, say an hard disk, when it was exceeding the amount of memory needed. So the programs become really, really complex. just to make an example, the language tech that you may have been used for typing scientific papers was written by Donald Knuth, and since when it was planned, the not Knut had the goal of having something that worked the same on any hardware, but the management of memory was not the same on different computers. So he decided not to use any kind of, say, virtual memory, and so tech is written with a fixed amount of memory, so not allocation, the allocation of memory. The whole management is done with a fixed amount of memory. Clearly, he had to rewrite all management of memory. But what people started to do was to have some circuit, hardware circuit, and also clearly software, being able to, when you ask for more memory than what was physically available, to fake the computer saying, okay, I'm giving you the memory, but actually what you do is to dump, not use the memory on the disk, for instance, and free the space and give back to the software, the program that asked for it, the pointer to the new part of memory. Clearly, this includes managing all the pointers to memory in a smart way, in order not, first of all, not to lose a lot of time in dumping memory back to the hard disk and then loading again. And this was a real innovation. Clearly, I remember, for instance, when I was working in the engineering department, in the engineering faculty, that since I was considered the one who could solve some problem, I had a lot of students asking me, I don't understand why this MATLAB program works well until n is equal to 100. When I put n equal to 1000, it stopped working. What happened was that it was using virtual memory and started so swapping memory from the disk up and back. Okay, and so the other point is that even though you had small, slow bulk memory, so hard disk or DRAM memories, it appeared to be much faster because if the management of memory is smart enough, you are essentially always or almost always using data that are in the RAM instead of that contained in the swap. At that time, also there was the invention of the most sleek and elegant computers that ever existed, the Cry, which was like this. Actually, this upper part are the part needed to cool the computer, and there was this nice sofa all around, so you could sit here waiting for data coming out. And this was a really powerful machine that inaugurated the era of vector calculation. You remember that in many cases, in physics especially, you have to perform the same computation on all elements of a vector. So this was especially done in such a way that we could do this in parallel without rereading the instruction for each units, but simply applying this in parallel, almost in parallel, to all elements of a vector. And clearly this opened a complete different way, for instance, of storing things in memory. It was crucially different if you store, for instance, a matrix row wise or column wise. So, for instance, sometimes it was much faster, first to transpose the matrix and then perform a multiplication than doing it in a scattered way. And the other points that will become more and more important in the future was that the length of wires become the the main point for the speed of computer. The computer was so speed, well, not so speed, 10 megahertz, but it was speed enough, fast enough that the length of the wire become important. So clearly, in this case, you have to change everything in order to pack, to shorten the length. But this means also to have problems in cooling. So this machine, for instance, used the freon cooling, so essentially like a refrigerator, in order to keep things cool. And the other part, the other things that happened at the time was that small and relatively cheap computers start to appear. Also, IBM, which was targeting the mainframes, started to offer small memory, small computers, generally using DRAM memories, at reduced prices for university, because they needed a lot of computer programming. So they were trying to induce people to start studying computer and computer languages and so on. And this started also to to have people with free access to computer, nothing to do, or not willing to do what their supervisors told them to do, started to produce, for instance, ASCII art, in this case Snoopy, which was, as you can see, printed on a sheet of paper, because screens were not so common. 62 is also so in some sense, the end of an epoch, because you can imagine IBM finally started to make more money selling computers than selling punched cards. So cards to be punched. So, for instance, these are other examples of ASCII art. If you want to see a really big workplace never completed, you can watch at the first, I can show you, the first steps, so the first few frames of Star Wars, completely designed using only the ASCII characters. So you see, this is episode 1, New Hope, and you have the whole adventure redesigned, with the two drones and he's cleaning itself. I don't know if you remember Star Wars. It is already 30 years ago or more, but you can imagine each of the frames are drawn using ASCII character. Clearly, it had some way of say reusing elements, but it was a piece of software. Okay, and as I anticipated, women also from the era of ENIAC, because also in ENIAC and also at the beginning of computation, women were used as human calculators, and also at the time of ENIAC they have been used as programmers. Programmers means rewiring the ENIAC. And then they started to become programmers in the usual sense. They mean writing program code. Clearly, they started also to differentiate from analysts, normally males, that gave the infrastructure of the program, and women programmers that translated this in paper, essentially. And as I said, the system 360 from IBM was something new because instead of just building a computer, IBM built a complete universe. So not only the computers, but also the reader of punching card, the tape driver, the disk storage, the printer, the keyboard, the audio response units, I don't know what it is, data entry, and clearly display solutions. So, and you could also have more smaller computers that emulated the big ones using software, so that you could use the same program for one architecture and to another. You had not to rewrite your program because your computer missed some instructions. And this was also clearly something that now we are accustomed to, but at the time it was really a revolution. And so you can see this. And another problem at that time, since finally a hard disk appeared, was that it was the management of a hard disk was essentially different from that of, say, punching cards and tapes. Let's consider tapes. I worked very little with tapes. With tapes, you had to say, okay, tape, please, the tape control, please go to meter 1962 and read a certain amount of data. Now, so you have to keep track of what was inside the tape. There was no directory in the tapes at the beginning. Then clearly in the cassette type, they used to say at the beginning what was inside. But in any case, it was essentially not really usable, because in order to understand what was inside the tape, you had to go to the beginning of the tape, read the directory, and then maybe go to the end. And tapes were not so easy to be unwound, because, for instance, again in the LEA, there were tapes. They when they tried to run at high speed, they tend to tear the tape, and so, for instance, they use jets of air in order to make the tape float and run smoother in a more smoother way. So it was nearly complex things. While for a hard disk, it is like having a lot of small tapes in parallel with the head that can go from, say, they are not tapes, they are cylinders, but this is essentially the idea. So a hard disk is a certain number of plates and a set of heads that can read and write from the two surfaces of each plate. And then they can move. So the plate is running, so you can just wait until the data is passing behind your reading head. But you can also move the head inside in the other direction, so to go from one cylinder to another one. So clearly, first of all, since you are not controlling the turning of the disk, you have to organize the data so that you can read and write them at a certain, depending on the speed of the head, in certain positions. So, for instance, if your writing is fast enough, you can write things one after the other in the disk. But if the head is low, you may prefer to write data in alternating way or one every 3 data, in order not to lose, not to have to wait for the disk to make one turn. And so they had to do a lot of new innovation. But the important point is that now it is extremely fast to jump from one point to another one of the disk. So it made sense to have in some way the list, the directory of what was inside your disk. Clearly, at the time, files has not been invented, only records. So you may have a directory of what records are inside. Clearly, each record of the same size. So you may say, okay, the data of this experiment start from record, I don't know, 5,000 until record, I don't know, 10,012. And so no console, no, you can see here, this is data entry, but not a console for driving the system. The system is driven essentially using punched cards. A different approach was that of Univac, in which they introduced the idea of having terminals. So the idea is now that if you, and this took time, if you can program or run your programs from a distance location, then where you put the mainframe is relatively irrelevant. And the other point, also everything happened in the 60s. The other point was about software. From now on, up to this time, the software was considered essentially the same as the software you have in your car. Your car has a microprocessor. No, you run a lot of different software when you say you do everything on your car, but you are not paying for this software, since you cannot neither install a new software nor use an alternative version of the software. And this was considered to be normal. IBM sold you a computer for doing a bank account with the necessary software, and nobody thought that you could either develop a new software or buy a software from a different vendor. So software was not considered something that could be sold or bought. And also in the 60s, there is the beginning of Cold Wars. You remember now that the wars are clearly a powerful push to develop new things. What happened with the Cold Wars? See, Dr. Strangelove is a 64 film, which is worth to be seen. So the idea of Cold Wars started essentially when, clearly after the Second World War, but the main point was 1961 with the Sputnik, and also then Gagarin. I don't remember Sputnik was a 60 or 61. So the idea was that up to that time, United States were dominating with the strategic bombarder, so that they were not concerned about the Soviet offenses. But with the development of intercontinental missiles, they suddenly realized that the Soviet Union could send a missile from Russia to United States in, say, half an hour. So they had to rethink everything so that to have a way of detecting and reacting to something within this amount of time. And so clearly they needed to use computers. Also, missiles use the computers. Clearly, for instance, the Soviet ones used the valves, vacuum tubes. while in the American ones, they started almost from the beginning to use transistors. But the idea was that how can we interact quickly, for instance, in a 2 or 3 dimensional environment in order not to drive a counter missiles against the incoming one. So, for instance, they developed optical guns like this one, so that work in the way, since the pattern in a radar screen and also in the computer screen was written line after line, where if you have a sensor which was synchronized with the writing, this had, so the time for which something is drawn on the screen gives the computer information of where the gun was pointing to. So you could use this information in order to have something that moves following your guns. Actually, it is you move the gun, so when something is written is read from the gun, the timing of reading sends to the computer information of where the gun is pointing to, so that you can then draw some symbol on the screen on that point. And so, okay, so 61 is Gagarin, but 57 is Sputnik 1, and so this was the signal to United States to invest in astronautics and rockets and so on. So, for instance, the NASA was founded in 58, and in the 1960, von Braun, who had developed the rockets for the Nazis, became the head of the Marshall Space Flight Center, and then the head of NASA. Now, with this kind of problems, for instance, astronautical travels and also clearly strategic missiles, you had to develop a different type of computers. As we shall see, computers now had already adopted the idea of interrupts. Interrupts means when something happens, say that require attention. For instance, when the data from tape are available, because you send a command to the tape reader, it takes time in order to rewind all the tape and find the data. Then, in the meanwhile, computer can do other things. When data are ready, and so they're arriving because you don't want to stop the tape units, you need to tell to the computer, okay, stop doing what you have been started doing, and now you have to process this data. And this was done using the interrupts. But in a crucial system like Apollo missions or nuclear rocket or also industrial machines, this is extremely dangerous, because if you receive an interrupt while you are doing something fundamental, it may mean to have the rocket to crash on the moon and so on. So you had to develop a completely different type of managing the scheduling of tasks, and so the real-time computers has been invented essentially for these reasons. And for instance, in the Apollo mission, they used the modified IBM system in order to have the first computer. And at that time also, Olivetti, which has a very complex history, started to work. For a certain amount of time, Olivetti seemed to be one of the leading computer enterprises in the world. And because you see that at that time, so before the 60s, they developed this Lea 9000 family, which was in Bibbiena there is one that you want, if you want to look at it. It is extremely interesting to go there. There is a room full of this rack, full of this card containing a few transistors, with an incredible amount of noise for all the fans used to keep everything cool. And so, for instance, it was a transistor computer, but used a lot of tubes for power supply. I don't know if I have no image, but there are a lot of these racks that simply essentially furnish the voltage for all the transistors, and they use a lot of tubes for this. Clearly, it had no keyboard still, but only a number of symbols that corresponded to different tasks. And this was a funny history. If you want, you can read the book by Giorgio Perrotto about the history. What happened was that in the 60s, Adriano Olivetti, the founder of Olivetti, died. Someone said because it was killed by the Central Intelligence Agency. And also Mario Chu, this Italian Chinese engineer who was the head of the computer department, had the year after this a car accident again. There are people suspecting IBM. And so at a certain point in Olivetti, clearly Olivetti was born to produce typing machines. So there were a lot of people who was expert in mechanics, but very little in electronics. So at a certain point, after the death of Olivetti and Mario Chu, a lot of people started thinking that it could be better to close all the electronic departments and come back to what we know how to do well, so typing machines. So at a certain point, they sold everything to General Electric. But fortunately, Giorgio Perrotto, who was an engineer there, had developed this small, essentially home computer, and he was smart enough to term it not computer, but calculator, so that it was not sold to the General Electric, but remained in Olivetti. And this was a small computer. It used for the central memory a wire, a rounded wire, that had a delay line of containing about 1,000 bytes, with a time of about 1 millisecond from the start to the end. And then he had a language, programming language, which was essentially numeric, more or less used a certain number of symbols. So you can see here. So you had the letters, so they correspond essentially to registers. So you can say, okay, put this number into this register, put this number into another register, add them, and then read another things and put this in another register, and so on. Print, etc., etc. They had the idea of using this card on a magnetic sheet of paper, so that you could insert them and use it like a floppy disk, say, to store a computer program that can be read after time. And clearly they had a printer here, Olivetti, so they know very well how to make a printer. And it costed about $3,000, which is about 30,000 euro now. But it was programmable, and it could use more of this floppy disk. So you could insert first a program, do something, then insert another program while keeping data on the the register, and so you could continue your computation. And actually, it was used by NASA for some part of the Apollo mission, and as you can see here, more than 40,000 units have been sold. Okay, so this was the end of the Italian contribution to this world. On the other side, instead of the big approach of IBM, some others mini computer enterprises appeared. Mini means that it was just like this, small cabinets, not a whole room, but still big. So, for instance, one of these, which became famous in the following years, was the Digital Equipment Corporation, which PDP-1, this was the screen. They had this teletype for entering program, and the Digital Equipment Corporation, so the DEC computer, were really a revolution, because since they had no resources to produce also the program, they started, so first of all, selling these things to universities and encouraging people not only to play and try, but also modify and propose a modification to the hardware, so that essentially they recruited a lot of enthusiastic people in university working for nothing, furnishing ideas and developing new pieces, which was clearly completely the opposite of IBM approach. And so this PDP-8, which at the end was just one cabinet, everything inside, also including, for instance, the type reader, was really the first home, not home, but personal, in some sense, computer. So you see that university could allow to buy one or two of them, and so also IBM at a certain point, as happened later with the personal computer, started thinking of this market. So they also produced a mini computer, but could not compatible with the system 360. But the idea of IBM was not to sell, but to rent. And clearly, for some university, instead of spending $10,000 and having and owning a computer, they may prefer to spend $1,000 per month. Clearly, after a year, it was more than the other price, but maybe for the budget, it was more accessible. Have you said, I said that this is, for instance, one of the idea of one of the cards at the time. You can see here resistors, capacitors, and this is probably a resistor. This is a transistor. So you can see that you need a lot of space and a lot of work to assemble these things. Clearly, the first innovation, which you can see already here, was the creation of, so the introduction of printed boards. Printed boards are something that a piece of resin with some metal, so some copper over, then a layer of copper, which you can say protect with some kind of wax, then put into an acid bath so that copper is removed, but not where you protected this, and so you can draw your circuit, and then clearly you have to make holes and to solder your components on this. And clearly, the advantage of this was that instead of having everything on a big board, you can also have connectors so that you can replace failing scars with another one. and you shall see in the following that there were also computers completely based on a backbone made just by a bus, with everything on cars to be injected. But in the 58, Texas Instruments began to study the possibility of making an entire circuit on a chip, integrated company. And so the idea is first to have a package containing some amount of logic gates. This is the idea is that, so you see, 10 years has passed. The idea is to have design everything using this kind of architecture, which is called the TTL architecture. It means that you have a transistor here performing something, essentially a gate, and then a second stage with another transistor that provided enough fan out. Because the problem of building a circuit is not only to design the logic in order to have what you do, but then you have also to be careful on how many. So suppose your signal is exiting from one gate, then you have to, in general, be careful on how many other chips you are attaching to this one, because every chip uses a small amount of current. So you have to be sure that your output, power of your chip is enough to furnish the current to all of these following circuit. The idea is that if you have a dedicated transistor to provide this current, you can have enough fan out so that you are less worried on how to design your circuit. And at the time, 64, also the idea of dual inline package appeared. So this standardized the design of a motherboard. So this is clearly a board for testing a circuit, but this is for instance, this is Arduino motherboard, in which you can recognize just one at the time dual inline chip, and these are Fairchild, I think. Gates probably using these dual inline things. Now, these again military demands shaped things that now we are accustomed to, but was not clearly normal at the time. For instance, redundancy. The idea is that in critical missions, you cannot trust a single computer, so you have to use maybe more than one, but how many? But if two are not enough, because I suppose that they give different answers, how can you decide? Clearly, it is enough if you are only considering failure, complete failure, but suppose that some cosmic ray has damaged some memory element, so that one computer reads one and another reads zero in that position. Who can you trust in? So in general, you use at least 3 or some odd number, so that even if they give a different answer, you can use a majority rule in order to say you take a decision. Clearly, separation of functions, instead of having one big computer who controls everything, if possible, better to have different computers, smaller computers, to work on different subsystems. For instance, in the dramatic phases of Apollo 13 mission, you remember the one in which soon after it was planned to land on the moon, but after sometimes the one of the tanks exploded, so that the crew had to leave the main module and go into the lunar module, which was supposed to descend on the moon, to stay there, to save power and to save what can be saved, because otherwise they would not have enough power to reheat the parachute for coming back to the Earth. But also the computer of the command module was consuming a lot of power. But fortunately, the lunar module had its own independent computer, so that they could use this one clearly, who could use the much less power. And clearly, also software engineering become a new discipline. So how to write a code or to use a particular languages in order to be relatively sure that at least the most common problems, I don't know, memory leakage, so a piece of memory that was allocated by one part of a program but free from another part before the first part was completed using it, and so on. And finally, computer controlled device, because human reaction time was too slow. For instance, the shuttle in the 70s was not maneuvered by man, because it had to react too fast, regardless of the movie. The one on which they go with Bruce Willis to make the asteroid explode. I don't remember the name. But in any case, at the end, in this movie, or maybe Space Cowboy, they used to drive the shuttle by hand, but it was essentially impossible. They had to use a computer. And the other, so I'm trying to cover all the invention of these times, and so they tried to, especially when you had the mini computers at hand, they started to have to develop interactive interfaces, and clearly one of the first things to do with the interactive computer are games. So, for instance, at that time, Space War, which was a game in which war asteroids, where the invented. This is, you can see here, it is a PDP-1. Were invented in order to, first of all, to amuse programmers, and also to test, to develop new things. You could, they invented a kind of a scratch pad in which you could directly write on the screen using an optic pen. And also the idea of what was learned with mini computer, that people needed to practice, finally penetrated also the world of mainframes. But the problem of mainframes was that you could not have a mainframe, say $30 million at your disposal to play and to test things. So that they developed the idea of having more people using the same computer at the same time, using the concept of time sharing. So the idea was to have several terminals, first of all, connected to the same computers, and have a computer that dedicated a small amount of time to each of the tasks. For instance, the task could be the program that ran the terminal, or the program launched from a terminal, so that each user had the illusion of having a dedicated computer, while the computer was instead just one, but appeared like more than one. So clearly, this first of all, allowed the introduction of, say, student languages like the basic. Basic, I mean beginners, all-purpose symbolic and structured code, which was invented not by chance in a Dartmouth College, but also computer like a public public services, so that you could, they started thinking that you could rent not a computer, but computer time. So I want, like we do now, I want to play, I want to learn, I want to launch a program. Instead of buying a computer or renting a computer, I can just rent a computer time. And so the basic is essentially almost Fortran, no? But instead of being compiled like the Fortran, the original basic was interpreted line by line, so that you could use, so essentially the program, I don't know if you ever programmed in BASIC, but it is that the program is just a script of lines that you could also enter one by after the other, so you can test and play, and then you assemble them into a listing in a file, and this is essentially a computer. And clearly, as we have seen for Lisp, so that there was computers explicitly designed to run Lisp, this happened also to BASIC. And in some sense, it became the standard. If in the 80s you bought a home computer like the IBM PC, the Apple II, and so on, you expected to have essentially free BASIC already installed, sometimes directly in the ROM of computers. And okay, so we have to we are now essentially so in the mid of the 70s, you had essentially all things that we are accustomed to. The idea is to have multitasking, also preemptive multitasking, so that you don't have to say anything because everything is managed by a computer system. Still at the level of so mini computers, these took a lot of time in order to be ported to home computers. And also, clearly, the idea of being able to remove an hard disk without restarting the system. And the top of all of this was essentially the DEC PDP-10, which was really the standard of computers. So, for instance, Bill Gates, at the age of 15, started to work on such devices just to fix bugs. And this was essentially the growing of such a world, which was still missing essentially the problem of the operating system, because up to now there was not such a standard like an operating system. And so this was a crisis, at least it was called a crisis, the 68 crisis of software, because, for instance, Dijkstra, which is a physicist that known for his algorithm for finding the shortest path, if I remember well, on a network, and started to think how to build from the scratch the architectural computer in order to, say, put together all the needs that emerged in this sense. So, for instance, the idea of semaphore for a resource, that you have some device that if this resource, that can be memory, can be an external device, is unavailable, you don't simply say, okay, this is not available, you can crash your system, but you put the task in a queue, and clearly you give this time to other tasks. And when the software becomes, or the resource becomes available, the threads in the queue start to be executed. This meant starting thinking to a program not like a monolithic things, but made by threads. So the idea is that you have to do something with this data, but also something with other data. Okay, instead of doing first this and then the other, so that if the first one is not available, you have to stop, you try to develop parallel, essentially, threads, and use a semaphore, because the rest of your software could not be run until the two resources have also both completed the task they had to do. And this is essentially also the birth of object-oriented programming, so that you could not to have, so for instance, suppose that you have organized the data related to something, I don't know, to some object, some database or something like this, so that you have a certain number of internal resources. So for instance, just think to a file. In order to access a file, you need a pointer that says where you have read up to now, so that you can start reading the rest. You have permissions, and you have a lot of different things. All of this data normally stays in something like a structure. But in general, for instance, using the C language, this data, if you need to make them public, so the address of your structure can be addressed by some part of software, this meant that you can also manipulate the internal data. But as far as the single programmer has written all the software, okay, this is his task to keep track of everything. But now that you can have several programmers working, say, on different pieces of the same operating system, and so maybe one has to do something with the data, the internal data of this structure, he could, because I have not read all the documentation carefully, for instance, put some inconsistent data, so that, for instance, have the system to crash. It happened, for instance, to have a satellite failure because of some data badly written in some record, so that one engine started not in the right time. And the solution was to develop languages that naturally forbade to access internal variable, and only allowed the access to the right one through methods, not directly manipulating variables, but asking the right method to change some value, so that the method designed by the writer of the object could check if everything is okay, and so on. So essentially, this is the idea of object-oriented, and the birth of languages like Simula, which then originated all kind of object-oriented languages. Clearly, the other aspect of this is that you instantiate an object, but you don't want to count if this object, to keep track of this object, if it is still needed, and in case it is not needed, to release the memory allocated for this object. So the idea of garbage collector started that, for instance, keeps tracks of how many pointers are still alive pointing to a given object. If no pointers exist pointing to a given object, this can be safely destroyed. The danger of garbage collector is that you never know when it will start revising all objects, so that, for instance, you cannot use this approach in real-time computers, because if a garbage collector starts at the wrong point, you have a system that freezes just because he's managing all the memory. And okay, so here is an example. No? For instance, you are writing a graphic interface, you want to manage a rectangle, you need to store the coordinates of two corners, but you don't want to have these rectangles drawn in a different order, because it could, say, for instance, turn everything inside the rectangle upside down. So you have to be sure that the first angle is the top, I don't know, top left, and the second, so the first data top left corner, and second data at the bottom right corner. And when you say grab the wind, you may need, for instance, to switch these two data if the who has was drawing the rectangle has crossed these 2 points. So essentially, this is the idea. Okay, I think that we can stop here for today. You are quite bored now, I think, now. I don't know, let me see. Okay, maybe I can just 2 slides. If you want to bring this concept to the extreme, you have to give a look to Smalltalk. Smalltalk, again at the beginning of computer era, was the extremization of this concept. In Smalltalk, everything is an object. So, for instance, 1 plus 1 is not simply an instruction to sum 2 numbers, but in Smalltalk, 1 is one object. Clearly, it is an object of the class integer number, which is a subclass of integers, or maybe positive integer number, which is a class of integers, which is a subclass of numbers, which is a subclass of ordered sets, and so on. Plus is the message, and 1 is the content of the message. So in some sense, if you switch these two in Smalltalk, you are doing something really complex, because it converts a message into an object, and an object into the body of the message. So, but clearly it makes easier to deal with classes, subclasses, inheritance, and all these kind of things that probably you already know of object-oriented programming. Then Smalltalk was never, although I studied at the time, so several years after, because in 1970 I was 9 years old, so I was not still studying computer. But I remember having been fascinated by Smalltalk and this idea of everything is a message, also because it had a kind of a graphic interface very similar to the nowadays notebooks idea. But it never was a successful piece of software, but still is living in this quick open source version now, that if you want, you can play with. It is quite used to teach computer science to childs. And clearly, from this the beginning of object-oriented computer, all what you know now, C++, C Sharp, FL, Java, JavaScript, Visual Basic, Python, even Fortran and MATLAB now has the idea of of object-oriented programming. But for instance, Linus Torvalds always refused to use object-oriented programming for the Linux kernel because in some sense, object-oriented programming was done in order to protect software, say, operating system, large softwares, from damage that can be done by someone who started to who writes a piece of software in order to interact with the already built corpus without knowing the minimal details what the software is doing. And Linus Torvalds said, okay, if you want to put your hands on the Linux kernel, you have to read all the code first. So to understand exactly what each piece of the kernel does. And actually the source code of the Linux kernel is quite readable because of this. So people put a lot of effort in order to make the code readable so that you can safely manipulate internals because you know what you are doing instead of doing the opposite, not pretending that all people know what they are doing, but instead putting obstacles in order to protect the rest. Linus also complained because he said, okay, suppose you are using object-oriented programming. So you have object for manipulating, I don't know, memory or something like this. Then at a certain point, a computer programmer needs to do something new with this piece of, say, hardware. You cannot alterate the existing objects because it can break everything in the system. So you define a new object which is exactly the same as another one, plus a new class, say, with another exactly equal to another one, but with some element more. So you have a proliferation of almost identical classes, which are extremely difficult to be maintained when, say, you want to update your system with a new version of the kernel. So instead of this, I say, okay, read all the code and then propose your modification when you are competent enough. Okay, I think that we now have to stop, and the next time we go a bit further in the development of this computer world. Questions? No questions. Everything was crystal clear. Okay, if you don't have questions, I can stop recording and